And I want to start with something that's really kind of freaky to illustrate how probabilities are not something that's inherent in us to understand. We only know enough probability that helped us to survive so that our species can continue. So back in the day, the caveman walking along, he's like, "Ugh, sun here, saber tooth there, I'll go this way." So he knows the probability if he goes this way is better that he'll survive based on past experiences with other people. So that's about where our inherent understanding of probabilities are, which is not very far at all. So we did the birthday thing, remember? So that's kind of like counterintuitive that there could be so many in a group of people that have the same birthday. Sleep. Oh my God. Poor little guy passed out. So I'm going to start off with a really freaky example. It is freaky. And some of you guys might have heard it. It's called I call it the Monty Python problem. It's the Monty Hall problem. And it goes like this. There's a show called Let's Make a Deal. Used to be hosted by a guy named Monty Hall. Now it's hosted by, I think it's Wayne Brady or whatever. Thankfully I don't watch it. But at the end of the show, there used to be these 3 doors. And the host would pick somebody who won a lot of money and say, you can trade in all that for a chance at the 3 doors. So behind 2 of the doors were mutant goats. Right? I say mutant because I'm going to draw them and they're not going to look right. And we're going to assume that somebody didn't go on the show to win this goat. Are you with me? So that's a bad thing. And behind the 3rd door is like $50,000 or an all expenses paid trip to Switzerland or something. You with me? So there's one door that's really good. So here I got door number 1, door number 2, door number 3. Somebody pick a door. 2? I heard 2. I heard somebody say 4. Did that just happen? Door number 4. You have lost. Thank you. We'll see you guys next time. It's like you leave with nothing. Good job. All right. What is the probability, if you pick door number 2, what's the probability that you have won already? Let's be less specific. Or actually, it's not even specific enough. You want to give me that answer? Keep going. No, okay. Probability that you won. Well, how many prizes are there?
3.
How many prizes are there? 1 prize out of how many possible things that could happen? 3. So 1 out of 3. Is everybody cool with that? There's a 1 out of 3 chance you're going to get that big prize. So right now, there's a 1/3 chance that you don't want to change doors, that this is a winning door. You with me? What's the probability that this didn't win, that the prize is somewhere else? 2/3. I like it. So far, this isn't anything crazy, and I said it was really weird. Well, here comes the weird part. So what would happen then is the host says, all right, let me open up door number 1 and show you, oh yes, mutant goat. Spider goat. Okay. He's happy. I think. Is he happy? He's happy. He's a happy little mutant goat. He glows blue in the dark. So I open. No, stay with me. I'm sorry. Let me come here. You picked this door. I open this door and show you the goat. Are you with me? And then I say, do you want to switch doors or stay? Is it better to switch a door or to stay? Or does it not matter? It is better to switch doors. That didn't change. Why did I open this door? Why did I open this one? Because if I open the door with the prize, show's over. There's no drama. There's no tension. You with me? And I need that so the people will watch, so they got to get commercials and I can make a lot of money and whatever. You with me? So I got to build that drama. So I'm going to open the one that they go. Now, what's more than likely? Did I win or did I lose? What's more likely? It's more likely that I lost. You with me? 2 out of 3 times, I'm going to pick a goat. So why did the host not open this door? What's the most likely explanation for why the host did not open this door? Because behind this door is the frickin' prize. More than likely. So right now, I know we're all confused. So let me do this. I want to show you what the actual problem is this. Now let me give you something that might be easier to understand. What if there were, all right, everybody, all right, no, I'm not going to draw one. What if there were 100 doors? No, Jeff, you could do it. There you go, buddy. My brain was like, I know how to count. All right. You guys with me? 100 doors. And let's say we picked door number 2. You with me? We picked door number 2. I, as the host, open up every other door to show a little freaky goat, except for door number 3, right? I open up all these doors, every single one, except for door number 3. Does it make more sense now? Because what's the probability that we won? No. From the beginning, when I picked door number 2, what's the probability that we won? 1 out of 100. There's only one prize out of 100 doors, right? You with me? So there's a 99 out of 100 chance that it's behind some other door. So when the host opened up every other door, that has got a 99 out of 100 chance to be the prize. It is much better to switch them. Does that make more sense? I mean, if there's 100 doors and I open up every other one except door number 3, shit, yeah, the prize is there. What's the only chance that it's not there? 1 out of 100 chance that I just happen to pick the prize first. Right? Here's another, real quick. You guys know that stupid show with the suitcases in it? Yeah, there it is. Let's make a deal. Deal or no deal. So if you picked a suitcase and then they were like, we're running out of time, let's just change the way we do the show. Open up every other suitcase and none of them has the highest prize and they leave 24 unopened. What is in that freaking suitcase? Freaking the biggest prize, right? Well, that's the most likely thing. It's very unlikely you pick the biggest prize. They opened up everything except that one and they're like, you want to switch? I'm like, hell yeah. It's a very small chance that switching is bad. Okay, that's enough of that. That's enough, sorry. So the whole purpose of this is not, hey, this is the kind of problem you're going to do. That's not what this is. This is, hey, here's why probability is freaky, right? Because when I do this, people think there's a 50% chance now. That's crazy. There was new information. I'm the host. I know everything. So why did I open that door? There's a reason I opened that door. More than likely. 2 out of 3 chance that the other door has a prize now. Okay, enough of that, enough. Go ahead. Spider goat. Does whatever a spider goat can. All right. So, let's bring it back down. Let's talk about stuff that we're actually going to have to work with. Not doors and goats and stuff. So here's the kind of problem. So we're making a big transition. This is exactly the kind of problem that I love to give. Quizzes, tests. I just go crazy with this kind of problem. It's called a contingency table. And it looks like this. Let me make a better example. Let me see if I can make a better example. You can do it, Jeff. Sure, that'll work. Yeah. Oh my God, Jeff, what are you doing? All right, that'll work. We'll make this work. Yes, okay. So I ask a group of teachers and students a question. And then I write down how many yeses, nos, and maybes, right? You with me? I'm not going to even say what the question is. I'm going to let you guys figure out what the question might have been. So let's say 80 teachers say yes, and 7, and 3. And then we got 11, 102, and 9. Sure, I like it. So apparently the teachers are in favor of this thing, whatever it is. Okay, I like it. So pretty cool with that. So how many students said maybe? Yeah, can you guys read my funky ass 9 or something? Yeah, 9 students said maybe. You guys see how to read this chart? Everybody with me? How many total students were there? Beautiful. So let's put those out here. 122 there. How many total teachers did I talk to? 90. How many people said yes? 91. How many no's? How many maybes? 12. How many total people were there? Yeah, 212, right? 212. You with me? Just add these up. Why do you think somebody might put a 424 here? If you add these people to these people, why does what I just said make no sense? These people are. These people, aren't they? So I don't have 2 groups of 212. I got 212. So a nice way to check is this better be 212 and this better be 212. And thank God it is. All right, let me stop for a second. Is everybody cool with this? We're going to do a bunch of probability problems right now based off of this data. I like to make a table like this out of the data you provided me in the survey that I wish everybody would do. That'd be great if you guys would do it. I keep forgetting to send out nag emails, but if you haven't done the surveys, do it. Please. All right. We're going to do a lot of probability questions. Have I given us any probability formulas yet? No. Because the basic idea of probability is based on counting. It's just based on counting, right? So for example, if I roll a die, what's the probability I get a 5? Well, how many sides are there in a normal die? 6. And how many 5s are there on the die? So I got a 1 out of 6 chance. There's one thing that matches what I'm looking for out of 6 total things that could happen. I like it. So whenever I say die, I might have a Dungeons and Dragons person out there, like with a 24-sided die, whatever. No, normal die, 6-sided. So here's the question: what is the probability if I pick one person from this group? What is the probability that I pick a student? I think I heard it. I heard a 1 out of. That's troubling. 122 out of, yes, sorry. So what the big mistake I get here is somebody says this, 1 out of 122. That's wrong. Don't write that down. But what were they thinking? They're thinking they want a student. They want one student and there's 122 of them. That makes no sense. What could I get? How many people could I get? Any of the 212. Out of those 212, how many chances do I have for getting a student? 122. I like it. So if you said that, I'm sorry. That's beautiful. All right, so help me out. Did I bring them? That'd be funny if I didn't bring them. I didn't bring my calculator. Oh, yeah, they are. Let's do this right now because we're going to need these anyway. Who needs a calculator? Calculator. Oh yeah, you like this one. Make sure it's got battery before you get too far away. Some kind of something. Yeah, driver's license work. All right. Require a passport next year. Okay. A real ID. You're going to need a real ID. So take a minute, throw that in the calculator, and round what you get to 4 decimal places. We're going to round all of our probabilities to 4 decimal places because we're all crazy. Oh, get down. could do that too. What do you guys get?
0.5755.
Do it again, sir. 5755? Yes, yes. Okay. I like it. So, I don't trust you guys. Yes, kick ass. Okay. So we call that not 5754. Don't just cut it. You got to round it, or else you're lying. So don't lie. All right. So that's not too bad, right? Not yet. What about, what's the probability that, where's the good one? Get out of here. That I picked somebody who said no. Yes, 109 out of 212. This is always the number of things that match what I'm looking for divided by the total number of things that could happen. Always. That's what probability always is. And then, whatever the hell that is. You could do it, Jeff. There you go, buddy. 5142. Yes. Now you could make this. What would this look like as a percentage? I don't care either way. Right. As long as you give me a 4 decimal place decimal, you can make it into percentage if you like. Humans normally like percentages, I've heard. Okay, I like it. So let's get something more interesting, because if I keep doing this, it's like we get the idea. Hopefully you get the idea. What about if I ask you this? So probably I pick a teacher or somebody who said yes.
101.
I love how you said that so confidently, and you're right. Let's figure out why. You were like, I know he's going to ask this question. All right. So I got, what is it that's going to be a match for me? Any teacher would be a match. And anybody who said yes would be a match, right? So let me say this. We're going to do some or problems. We're going to do some and problems. So we talk about or and. Or, so let's say I'm going to the club. Or is the nice doorman to the club that's going to let people in. And is the mean one. So here's what I mean by that. If I walk up to the club, that's the or club. He's going to say to me, all right, you can come to the club if you are rich, if you dress nice, or if you know Joe. I know Joe. Hey, Joe. All right, and then you go in. See, so the or lets more people in because you don't have to meet every requirement. You just have to meet at least one. And every time I say requirement, I sound like Elmo Flay. All right. And is the mean bouncer. So I come up to the and guy, and he'd say, all right, you can come to the club if you know Joe. I know Joe, and you have to be rich, and you have to dress. I'm like, you can stop. I'm out. I'm gone. See you later, Joe. Sorry, Jeff. Your guy's here on Wednesday. Okay. Do you guys understand what I'm saying? Have you guys ever applied for a scholarship of any kind? Anybody? Isn't there a list of requirements for some of these scholarships? I remember, so back in my day, all right, kids, let's go on a trip down Jeff's past. You'd go, I'm doing this because you would go to the financial aid office. This is before the internet really caught on, which is, I love the look I get sometimes. Like, excuse me? So before the internet caught on, we had these giant-ass financial aid books that they would update like every 2 weeks, and environmentalists would go insane because they're like chopping down a whole forest for the stupid book. So you'd sit down in the financial aid office, you'd have the crane bring the book over, and then you'd open it up, and I'd see, okay, good, math scholarship, you must be a math major, check, and you must have this GPA, barely, and you must do this, and then the last thing was, and you must be a woman. And this is a true story. I'm like, why didn't you put that first? So, and will always make probabilities smaller because fewer people meet every requirement. Or will make probabilities bigger because you're letting people meet any requirement they can. So you're taking in more people. Does that Makes sense. So or will always make things bigger. So I'm going to include the teachers. Now, what's wrong if I do this? 90 teachers plus 91 people that said yes. Yeah, so if I do the teachers and the yeses, have I counted anybody twice?
Yes.
I counted how many twice? 80. So I could do this. This is kind of silly, but right? I can subtract off how many I counted twice. Does everybody see that? I can't count people twice, no matter how much certain parties want people to count twice in elections or whatever. Matter. Right? So 90 plus 91 minus 80. Or you could be smart and say 90 teachers plus how many people said yes that I haven't counted yet. Right? If I do the 90 teachers, I got these people. So I only am missing that. So I could do 90 plus 11. But of course, what's 91 minus 80? 11. So either way you look at it, you get it right. Hopefully. Look at it one of those two ways. And what goes on the bottom still? 212. I like it. So then whatever the hell that is. .4764? Sounds about right. Cool. Okay. So we can actually write. Now look, we just did a problem about or. I didn't need a formula to do it. It was just the basic idea. But now I can write a formula for the general idea of or. So what is the probability of A or B? Where A and B are just whatever. It could be it rains tomorrow or my car doesn't start or something. A and B are kind of like the variables we use in probability to describe events. You guys with me? So looking back at what we did, I really want you guys to realize what we're doing. I'm going to create a formula for a situation that we already did without a formula, right? So a lot of the problems we're going to do, we're not going to need the formulas to do them. There will be some problems where I can only do it with the formula. So there's a reason the formula exists. So watch this. What was this related to? 90 out of 212. Teachers, the probability of teachers, right? So the probability of A or B is the probability of A, that's this, plus, that of course was the yes people, right? Plus the probability of the other guy, B, minus, what's this? What's the 80? Yeah, the probability of A and B. Those are the 80 people that do both. They're teachers and they said yes. So minus the probability of A and B. That is the OR formula right there. Written really bad, but oh well, you're used to that by now. So just to remind you guys, if I give you a situation where you have all the numbers you can count, you do not need any probability formula. In fact, very often it'll make it harder than it needs to be. They'll still work, but we don't need them. There will be problems when we need this. Situations where I don't give you all the stuff to count. Then I'm going to need the formula to plug shit into, right? Okay, I like it, maybe. All right, let's try another one. So let's look at and directly. Continuing my Roman numerals here. What is the probability that somebody says maybe and they're a student? So they have to meet both requirements. So how many meet both requirements? 9. Right? 9 people are students and they said maybe. Do you guys see that? So I understand the word and in English has multiple meanings. Holy shit. But in statistics, it only means that one thing. It's got to meet both requirements. So I could say you and you and you, and that's like it's adding, and then that gets in her head. That's not what and is. And is a list of requirements. You have to meet all of them. So the number should be relatively small compared to either of these. So, and also, and is often called intersection. We actually saw why a minute ago, but what's the intersection of students? What was it? And maybe. What's the intersection of students and maybe? 9. There. So and is often called intersection because it's the intersection of two things. It makes sense. It's almost too nice to see. That really didn't make sense what I just said. I can't look at it. It's too nice. So I get 9 out of what? 212. It still could be anybody. And then whatever the hell that is. I don't know. 0.0425. All right, so double check. Yes? All right. Did I need a formula to do that? No. There is a formula for and that is kind of gross that I don't want to use unless I have to. That is not a thing you're used to a math teacher saying, right? But that's generally the truth. Formulas are very useful in certain situations. In other situations, they are terrible. They make it seem much worse than it has to be. Okay. So, by the way, I'm not going to talk all damn day, thank God. I do have a little sheet. I'm going to stop in a minute and let you guys try the first part of it so that I'm not talking so much. I'm getting bored of myself. That's always good. All right, I'm going to take these away. I'm going to leave him for some reason. Have you noticed every bottom so far has still been 212? Of course it is. The only way the bottom could be less than 212 is if somebody told me something. So if somebody picked somebody and they said, I know this person said yes. So what if I said, what's the probability that somebody is a student given they said yes? So can you see how many people total am I talking about now? How many people could it be? Say it louder. No. Stop. All right. What do I know about this person? Let's start there. What do I know about the person? No. Let's read this again. You ready? Let's read this. The probability that they are a student, given they said yes. So what information am I given that they said yes? So, does everybody see that?
Yeah.
This is the probability they're a student. Do I know they're a student? No, I want to know the probability they're a student. If I know they're a student, that's 100%. Easy question. What the shit? Can't be it. The probability they're a student, given that they said yes. So how many people am I working with total now? 91. 91 people said yes. That's the only people it could be. If I said, I know they said yes, who could I throw out? All these people. Get out of here. Right? So my whole universe is this. Does that make sense? The only time the denominator will change is if I'm given more information. Otherwise, I don't know who the hell it is. It could be any of the 212. But here, it has to be out of the 91. Maybe. Do you see how the idea probably never changes? It's always out of the total things it could be. And if I know they said yes, there's only 91 things it could be.
You can't reduce it.
I don't even have a top yet. So I can't reduce yet. What will go on the top then? If that's my universe, let's probably get a student out of those people then. 11. I like it. And that won't reduce, but you can certainly make it into a decimal.
Amen. Yeah.
What do you guys get for that? 1209?
Yep.
Okay. And it makes sense because if I know they said yes, there are very few students who did that. So of course it's going to be a very small probability. So here's the next really freaky thing. And this is the last thing I'll say before I give out this sheet. Do you see how these are both questions about the probability of a student? Fundamentally, you guys see that? This is probably a student, and this is probably a student, given that I know they said yes, right? They both the probability of students. if I know the person said yes, does the probability, what did I put in here? Does the probability they're a student change? If I know the person said yes, does the probability that they're a student change?
Yes.
Yes. So let me say that again in a different way. Does knowing that the person said yes affect the probability that they're a student?
Yes.
You guys see how that's a yes? Everybody see that? So it's so beautiful that they decided to call that dependent events. Does the probability of student depend on if they said yes or not? Yes, it really freaking changes, right?
Yeah.
Almost 58% of them said yes, but only 12% of students said yes. So it's a huge change. Okay, maybe. So what would it take for two events to be independent then? Is if the given was the same as the thing was to begin with. So let me write that down. Here's what independent means. Oh shit, I'm using a symbol. This symbol right here, it's a straight up and down line. It means given. It's really weird. In my head, I see that as a word. So I will do that without even thinking about it. Math is another language. If the probability of A given B is the same as the probability of A, did A give a shit that B happened? Do you guys see that? So then they're independent, right? If you're independent from somebody else, do you give a shit about what they do? Yeah. Oh, Joe was over there. I don't give a shit, right? But if you're 3 and your mom leaves, you give a shit. You're dependent then. All right, maybe. So, is that cool? So in this case, does the probability of A given B equal the probability of A? No. So then I would say these events are dependent. People hear that and they think, no, they're not dependent because that doesn't have to happen for... No. Dependent is, does the probability change? Okay, I like it, maybe. All right, and we can do, I lied to you, and you should be used to that. I want to make, well, let's do this. I won't lie to you. I'll not lie. Let me give you this. You could do number 1 on this. If you want to look at number 2, you can. There's one side that says this side in class, and the other one is a practice probability quiz that I'll have an answer key for later. So do the one that says this side in class. You only have to try number 1. The course has many parts to it. Where were you earlier?